to do visualization and save animations and images out of it, it's useful to understand a little bit about digital image formats, because it can affect how you want to save your files, and it can affect the quality of the images that you save as well. So digital images have a data format that relates to what a screen is. So a screen has lots of pixels and it's composite color, I think. So red, green, blue, and transparency for each pixel. And that's what the digital image format just copies. So when screens were very simple and they had pixels, it was just it was a binary image, and you just had one pixel, one data value per, it was on and off for each pixel. And then we have real color, which is 24 bits per color. So 24 bits for blue, green, and red. And there's a transparency as well, which creates a color from the any color from the rainbow, which you can see on your screen. And you can also, if you look in image J or something, you can composite images from photography into each layer. So you'll have a green layer, a red layer, a blue layer. And if you're doing science, you might actually have images that just have blue in them, and you could use that as a way of segmenting or removing other data from it. So digital images, there's lots of ways of compressing your images, but all of them introduce artifacts. So most of them use issues around perceptual psychology of how your eyes work, and your eyes don't notice boundaries. In nature, boundaries would cover a lot of pixels or a bit of space, and so the images tend to be compressed, or there are problems with where the images are compressed at the boundaries. So you can see here we've got an image that has been repeatedly compressed and saved, and the quality is reducing each time, and the boundaries are getting more fuzzy. And you can sometimes see this on things. If you're saving images for your weekly review with your supervisor, good quality images you might get away with, but if it's for a conference or something, or you're going to put an animation on a website, I would always remove the lossy compression issues. There's a lot of the image processing software automatically sets your data, your images, to 95%, so you've got 5% lossy. If you read in the same file, edit it, save it out, read it in again, edit it, you'll find that over time your image looks like it's degrading, but it's because you've got the wrong settings on your image quality. So you should be aware of that. Also, a lot of visualization is actually more like a diagram, and that type of compression doesn't work very well for it. So you'll have even worse problems if you save an arrow like this, which is quite blocky because it's a very old image. You can start to introduce artifacts that just don't look good. And that's to do with the compression algorithm. So it might look great on the screen, and you look at the images that you've saved or the video you've saved, and you go, oh, look, the edges of everything looks bad. Well, go back in and check that you're not putting lossy compression into your images if that happens. So color is a really complex thing to understand, and visualizers and artists and always getting a lot of discussion about the use of color, but getting the right color in your visualization is great. And coloring of your objects in a visualization occur in the graphics card. So it's something that is computationally very cheap to change. So that makes it appealing for large data. So the physics of color is not RGB. The color has a different physics behind it. I'm not going to go into it. But the physics-based models tend to be based more on intensity, and then where in the rainbow wavelength and things like that, which is much more intuitive. So sometimes I'll change to a physics-based lighting model when I can't get the colours just right. And also saturated colours, which is to do with the physics of colour, can pop in an image. So if you want to have a saturated colour for an object that you want to draw your viewers to, you might want to use a physics-based model to pick that colour. So here are some of the screen colour systems. We've got the RGB, but the printer uses cyan, magenta, yellow. So when you see something on the screen, you've got to be aware that it might not print to the same way as you would expect. So it's always worth testing, doing a test print. And as we'll talk about later, always check that your supervisor has the same sort of colour vision you've got as well. And if they don't, adjust to your supervisor or the other people. So here are some of the physics-based models. And here we've got intensity of the light is a factor, which is the hue, I think, here. No, it's the value, isn't it? The value is how strong the colour is. And here we have another one with saturation. So one of the rules of visualization colouring is to have pastel colours, which is low saturation, if you've got a lot of colours. But if you've got one or two things that you want to show off, make them saturated. And then there is this thing called colorimetry, which will allow you to get the same colours in your screen as you've got in your printer. This is incredibly difficult to do. It can be done for, you know, really high-end applications or big screen films or whatever, but it's beyond what we do. So just printing it out and testing what you've got is important. And remember, your supervisor might not be in charge of printing out your reports and might actually have them all printed out in grayscale. So that's another issue you should be aware of. So here's a little bit on human vision. Visualizers get really interested in this. So the key point bits, it's an imaging system, your eye. It's got a lens, it's got a pupil, which is the aperture. The iris controls what the aperture is. And then at the back of your eye, which is probably the most important thing for the discussion of colour, you've got the retina and you've got the fovea. The fovea is where you focus the high detailed stuff in colour. And the retina, which goes across the back of your eye, is black and white imaging or night vision. And then the optic nerve, where that goes in, you don't have much vision at all. So those are the important things to remember. So the rods are for grayscale vision and they go across the whole of the back of the eye. They're only sensitive in low light. And yeah, so there's, and then your cones are in the fovea, which is where the high detail vision is. That's where your color vision is. There's something called twilight vision, which is where you switch from your color vision to your grayscale vision. Your grayscale vision dominates without you realizing. So it's not out, it's the value from the value area, the intensity of the value that you use in your pseudo color or your color map is the thing that your eyes are automatically drawn to. So using, well, we talk about that in a bit. So there are issues with wavelength of light as well and how you perceive that. So color differences that underlie the theory of opponent colors. So red and green are good together, black and white, blue and yellow, and you've got these different color models for that. And I think because the different wavelengths focus differently, so that can be a problem. So if you've got highly separated colours, they have different wavelengths, red and blue, and that will be difficult to focus. And the next slide, I apologise, shows you that. So you can see that these are not happy colour combinations. So when you're designing your visualisation, you want to pick colours that are so close together in the rainbow to show text and such like. So generally the fovea can't resolve small features in blue. So there's a group of visualizers who will avoid the color blue. And some people struggle with seeing blue. As you get older, your accuracy, the fluids inside your own eye turn yellow, so you can't see blue as well. Your brain tricks you and makes you think your eyes are all right, but it does actually get harder to focus on blue. So you should be aware of some of these issues when you're presenting your images to the general public or to particular people in your research group. If they've got problems with it, always ask, I think, is the issue. And here we can see visualizers just obsessed with all the possible optical illusions. And here is one of them. They're all actually moving at the same speed, but because they we're going from blue and yellow are both different wavelengths, so they appear to be moving in a jerky fashion, but they're not. So if you've got something that looks a bit odd, try changing the color in your visualization. I will say Paraview and the visualization community have put a lot of effort into defining what the best possible color maps are. So the color maps that come with Paraview are particularly good, and you shouldn't see anything. So this is one of the big arguments that people used to have in visualization, to do with color consistency. Should you use shading in visualization where you've got non-real color to show things? And the general consensus is that you probably shouldn't. And this is the example that shows why. We can see we've got it looks like a diagram, but it's a cylinder on a checkerboard with a shadow. And it looks like which checker on the board, A or B, is brighter and which is less bright. And when we look at it, they're both exactly the same. So your eye can be deceived if you use shading models and such like in visualization. So that's another hot topic where we don't tend to do that. But then if you can't have shading, depth perception can be difficult. So in some visualization systems, to aid depth perception, you can turn on fog. So you put a fog into the system to give you an idea of how far things are away from you. I haven't seen that in Paraview, but it's a common one. So color blindness is important, particularly if you're trying to communicate to the public, and people working in global warming have particular worries about this. So there are lots of different types of color blindness. If people are in your research group, I just always ask them, but you can always save your images out and simulate what they look like to someone who's color blindness, which gives you an idea of just a general idea. It's good to play around with. I quite enjoy that. And there's a link there to a color blindness application that you can try. So this is the color mapper in Paraview. It's actually pseudo color. So it's the use of color to represent the data values in the visualization. It's not photorealistic, which is the other term used in graphics. And it has something called the transfer function, which relates a data value into a color. And this is seen as the color map. Paraview uses the American spelling of color, so beware of that one as well. And here we have a little picture of the the color map editor, and we can see the one on the far end is edits the color for the legend, and that's where we altered the formatting of the text for that. You can show and hide the color legend. This is really useful for the transparency, is mainly used for volume rendering, which is a different technique. Algorithmically, it's like passing X-rays through an object, and then you can make them invisible or not invisible to the technique. And this is a nice intuitive interface for that. And then you could write your own, and you can read in your own textual version of the data maps as well. So the bulk color map, as you can see, you can set the parameters. It's got lines in it. It's not interpolated between each color. Is how you define that in computer graphics. And that means that the boundary between each color effectively is an isosurface. So if you can set those boundaries to particular data values, which you sometimes can by manipulating the limits of the range of the data value, you can get lines on your data which are very similar to contours or ISO values, and that allows you to not contour your data, and it can be a lot quicker. So that's a little trick that you can use with color and color maps. So it's the intensity of the image and the intensity of the data. Because of your night vision and how that dominates without you realizing it, image intensity is, people automatically relate image intensity to data intensity. So color maps that enhance that for whichever way you want to do it, I find particularly good. And good color maps, this was the result of the argument about color maps, and the rainbow color map in particular, which is the one you'll often see, that often has a dip in intensity in the middle of the color map. So when you print out images that have been rendered with the rainbow color map, it can be difficult to understand that image because the intensity in grayscale, there'll be two areas which will have the same grayscale value. So Paraview has done its best to get what is termed a rainbow color map that has even intensity across it. They put a lot of effort into that. So this is their well, it's not quite a rainbow color map, but this is a hot cold color map. But you can see in the middle there's an intensity difference. And then when you look at it in grayscale, it looks pretty good. It looks fairly similar. But if you didn't have such a color map, and this also is how it would look as printed out in grayscale as well. So you can use the grayscale image to work out whether it's a good color map in terms of the intensity variation across the color map scale. I think I've got a few images of this. This is a very saturated color map. People don't tend to like saturated color maps, but I think this one has variation in intensity in a couple of places across it. So it looks a bit odd, I think, in grayscale. I think you're losing some information on it. In actual fact, I think it looks easier to understand in grayscale, but people spend a lot of time agonizing over these decisions. Actually, you can see the boundary between the yellow and the red. There's a line in it in grayscale, and introducing lines into your color map, into your image, that can deceive the eye into seeing features where there aren't features. So you need to be careful on that. And here we have one that goes from low intensity to high intensity, dark blue to light, and then the grayscale is almost the same. And you can invert these color maps as well if that's what is better for your data. There's quite a lot of functionality. You can saturate to the end of the color maps as well. And here's just another one. So I'm encouraging you with these to try printing out your data in grayscale, so that you know if you're going to put it in your PhD thesis, and your examiners might print it out in grayscale, what they're going to see. So these are my guidelines. You'll find a lot of them online, and you can pick the ones that you want. So be consistent, always use a colour map that people in your area of science use. You want to be accepted, or your work to be obvious for people to interpret and be accepted. Generally avoiding saturated colours. If you're wanting a particular feature to pop, sometimes you can sneak in a bit of a saturated colour to do that. So if you've got multiple parameters that you want people to see, you can highlight them using different colour maps for different parameters. So if you've got temperature and pressure, you can use 2 different colour maps, as well as using different colour maps across different multiple related views. That will give you even more ability to understand how different parameters are interacting. Yes, black doesn't print very well. So what looks good on the screen with its backlit doesn't necessarily look good in printing. And Paraview has quite a good option when you save an image to save it with a different colour background. So it can be quite good doing that. If you do that, you might want to change your text colour to a dark grey, because the grey will show up on a black background or on a white background. So that's another good thing to do. Have good annotation, because once you've saved an image, it's quite often difficult to know when you saved it, what parameters you had. So I think the Paraview comes with a text animation thing, which will tell you the user, the computer, the day and the time that the image was saved. And that's on the image, and that makes it a lot easier to recreate that image in higher resolution or whatever for more important work than your day-to-day, where you're just trying to work out what's going on. And I never use lossy compression, and I use a lot of, so that's a data storage issue sometimes, but I prefer not to damage the images. So this is an area that I was talking about earlier with one of the questions. So visualization, design, I mean, with the exercises that we've got today, really we've sat down and we've just explored what happens when you use different modules. Once you're aware of what the modules do and what the key elements of the visualization or the data or the science that you want to draw out and present to your users or viewers of your work, you can actually sit down and design the visualization to do that. So how to create a visualization or set of visualization that presents information to the viewer or viewers that is useful and accurate. So that's really what you're wanting to get down to today. So we've not tried to do that at all today. And I go back to this at the very last slide. Most design models focus on the combination of data types and the information presented. Is there too much screen clutter, that sort of thing? Have I got a segmentation technique that gets the key information, make it more obvious? So I particularly liked a paper by Tori and Muller a few years ago, which was kind of a high-level taxonomy to look at this. But you also need to consider the computational efficiency and how interactive your visualization is. So I talk about that later on. And visualization design as a topic area doesn't consider pipeline optimization. So this was the way visualization was originally taught, with looking just at the data structures. So I'm not assuming that many of you are used to the way data is stored. I'm going back right to the basics. So binary is just a series of zeros and ones, which when interpreted can be read by a computer to give you float values of all sorts of integer or words or all sorts of things. The length of a unit of binary data is determined by the hardware. So about 10 years ago, 10, 15 years ago, we went from 32-bit architecture to 64-bit architecture on desktops. And you'll see that there's a lot of software that you can still download and install in 32-bit or 64-bit. That's what is being referred to there. And the binary data can be translated into all sorts of things, integers, floats, strings, text, any number of things. And an array, a lot of the data structures are in visualization are arrays, because you've got large numbers of data, and that can be efficiently stored and easy to manipulate in an array. And the arrays can be integers, floating points, numbers, or strings. Generally, it's integers and floating numbers that are used in scientific visualization. So here's a little picture of what an array is. So we've got we call it contiguous memory. So this is a bit of memory that's on your computer that's all one after the other. That's what it means to have an array. You have the index, which tells you how far from the start of your continuous memory you've got, and then you've got an element, and you've got a length of an array. So for example, if you had an array of length 10 and you went beyond the end of the array, you don't know what you might be picking up, and you probably crash your machine. Quite often happens. So these are the important things to remember. In data visualization, the data stored in each element is the things like temperature or pressure, and the index relates it to other. So you could have an array for temperature, you could have an array for pressure, and if they're at the same in the same index in the data, you know that it relates to the same location in 3D space that the simulation is working with. And all visualization and computer systems, OpenGL, works in a Cartesian coordinate system. If you want to use a different coordinate system like cylindrical or spherical, then you need to put an interpreter for that in there. So this is just laying the ground for looking at the Paraview data structures. And here you can see we've got an array which is just the dimensions implicitly tell you what size it is. So when you read that in, the dims would be 1, 2, 3, 4, 5, 6, 7. So it's a 7 by 7 array. And you could stretch what the array is. So if you know that that in real space is 10 nanometers, sometimes you can put that in. A rectilinear grid is just an array, but we've got another array which tells us what the spacing is between each of those. 3D scan data tends to be rectilinear because in the Z direction, the packing between the layers is different. So quite often that's a rectilinear grid. If you look at the head data, you can see that it's rectilinear rather than, this is called uniform rectilinear is the one. Then you've got coordinates. So you can see these are arrays, but each corner of those is different. So we've got a structured grid. Then we've got a point array. These are produced by laser readers, so laser scanners that scan the surface of things. You can get point clouds, but points can be a very low, computationally cheap way of viewing 2D or 3D data if you've got very large data sets, particularly if you're seeing them from a way off because the dots all merge together. And then as things get more complex, you've got your data arrays. So these strips of triangles are often used in computer graphics. And then you've got the cell data, and these are used in things like finite element analysis. It's the same formatting, so you should be able to transfer your data. easily. And so you've gone from here, which is just a 2D array, from here where you've got an array for the coordinates, an array for the data values, and then you've got a connectivity, so how you go around the coordinates to create a triangle, whether you go right-handed or left-handed, and that will affect the shading on the surface of your object. So this is just trying to be an example to show. So it's the information panel on Paraview that will give you information. So it says this is the head data set, which is medical scan data, uniform, rectilinear grid. So really it's just a 3D array with a bit of stretching on some of the axes to do it. And when you look at Paraview, if you look at these are the greyed out modules. The calculator is grey anyway, so that's not very good. But these ones are to do with more with fluid flow, and the head data set isn't relevant. So you can't connect them up. So greyed out modules, it's a data incompatibility issue. And so this is a second example. We've now taken the data out of the head, which was a uniform rectilinear grid, and we've put it into a contour, and it's become a mesh. So it's cell data. So it changes, and now we've got different modules that are greyed out. I think in fact, oh, it's just that one that's not that's greyed out. So that helps you work through what you can and can't do. And I just need to, some modules have multiple implementations behind them, so they can read in data from all sorts. So the contour module will read in all the different data types because it's got that behind it. So just because something will read in all the data types doesn't mean that it's easy to do that. That's all hidden from you, which is quite nice. So why do we have these visualization data structures? It's because it's easy for the visualization software to handle, but most importantly is because it's quick and efficient for it to pass that to OpenGL and to the display devices you've got. So in my view, I've seen a lot of simulations where you just have to flip one array or something, or the outside of a surface looks inside because the connectivity is going the wrong way round. So when you're building a new simulation, it's always useful to make sure that it renders nicely in a visualization system and you don't have to change it. So I would say that's something that you should do fairly early on in designing a new simulation, because once you've got legacy code that's been there for 10 years and is massive, changing the underlying data structures will become quite difficult, and it's an irritating step to go through, which is computationally wasteful. So we're back to, now we've understood a bit about the data structures, we're back, how would you design a visualization? So visualization is really about presenting information. Well, if you're doing it for yourself, it's about exploring the information, but then you take it to other people and you present it to them. So you can only use the data that you've got. And there's a lot of metadata that you might know culturally or for other reasons that are interrelated to that. So what other data can you collect, or what other knowledge that you can use? An example of that is in the example exercise sheet. We used the Celsius temperature system, because 0 is obvious for freezing, and we were looking at the freezing point of water. So there are other sorts of knowledge you can use, and you want to convey, I always look at it, you're really conveying a little story. And so what is that, and what techniques do you need to do that? And for the stuff I do, it's got to answer a research question. So the features you're drawing out are specifically ones around the research question. that you're interested in. So clarifying what the research question is and checking that you can see that is useful before you start running your simulation, because if you have to rerun it later because you missed a parameter out, it can be difficult as well. So now we've got a discrete or continuous design models. So this isn't about whether the data's discrete or continuous, it's about whether the design model is so a continuous model assumes that you can interpolate. So a digital image is discrete, but you can interpolate across it. So for the purposes of this analysis, we're calling that a continuous model. And a discrete model assumes that you can't interpolate. So colours of car, or you know, age. Oh, you could probably interpolate age, couldn't you? So an interval and ratio can be visualized as either discrete or continuous. So there are certain values or types of data that can, but nominal or named data, which is what I was trying to say with the name of the color, is definitely just one. I think that's a discrete one, because they can't be interpolated. So you can change between the two, but you've got to understand which model you've got to understand which visualization functions will be useful. So here we've got a table which probably explains this better than the last slide. You've got the design model is your data, or you're going to display it or use it in a continuous model or a discrete model. So a continuous is images, fluid flow, molecular structures, geographic data. And then these are the types of display attributes that you might have, which are distortions, structures, features, fisheye lenses, arrangement of numerical values. And then you can choose which ones you're going to use. So you can have time varying, regression analysis. And then discrete, which are probably the ones that are more commonly thought of as being part of information visualization. These are the types of things. So, well, air traffic positions, I guess that's a geographical one as well. Sunspots would fit there. Images can be seen, or segmented images can be seen as discrete. And you've got a different set of things you're going. So this is the high level taxonomy. You've got constraints in your display because you've just got a screen in front of you. So part of the way you can understand this is whether there's a spatial location that is important to the data, or whether the location can be completely the choice of the visualizer. So yeah, so most engineering problems have a space around them, but some more esoteric or mathematical ones might have a choice. But in some cases, the visualizer can choose whether you're going to give it a location or whether you want to put it next door to another value to see. So you can also choose color, transparency, and time. So here we have a taxonomy of continuous models. So we've got the 1D is a scalar line graph. 2D, Colormap, isolines. LIC is a lookup table or a particle tracer, glyphs. 3D, we've got volume rendering, isosurfaces. We've got tensors we can also see in 3D. And then ND, we've got multiple views or animations. So this is how the data structure limits what you can use in terms of filters or visualization modules. And then, so these are for the discrete ones, we've got much more like statistical plots, like scatter plots, bar charts. We can use Paraview. We could create a histogram of a 3D data set as well, which would be changing an image from continuous to discrete. So there are a number of different ways of doing this, which allows you to pick the right technique, or consider what techniques you could use. And then the given ones are the ones that you have no choice about. They just come with the problem area and the data set you've got. And then the chosen ones are the ones you can select. So continuous, you've got the spatial relationships and the numerical trends. So yeah, patterns, you're looking for outliers. And these are all in the discrete data structure area. So that should help you work out what types of visualization analysis modules might work for you. You can just play around connecting all the ones that aren't grayed out, connecting any filter that's not grayed out. That would also work, but this would allow you to give a more logical view of what to connect into your pipeline. So optimizing your pipeline. So having the right design helps you select the right visualization techniques. Once you have a good pipeline with everything in, it might not be optimized. In the worst case, it might not be interactive. It might just not be interactive, so people get annoyed with it. And you might be things that you can do to that will just make it interactive. So you can look at how you could optimize the data. For example, you could alter the size of the input data, you could clip it, you could contour it once you've clipped it, or if you don't want to change the contour value and you know that people won't mind waiting a little bit of time for the setup, you can contour it first and then make clipped options of that later on. And you want to look for the computationally expensive modules, and you can alter how it's triggered. So you might want to keep it so that you have to press apply each time. If you've got a few computationally expensive modules in the one pipeline, with Paraview, I would turn off the automatic apply and just change all the parameters you want and then press apply. So there are issues around that. So here's an example exercise. So this is around where you would be if you got to one of the later exercises in the first set. We've got multiple related views. We've got a lot of filters modules going on there. And you can see what we've got, how many? 9 clip modules, 2 contours, a calculator, and then we've got this text which gives us the information in the, well, we've got the environment annotation, which is the information at the bottom left, and then we've got a title as well. So it might be that we could, if we clip the data when it first came into the data set, if data size was a problem, then we could reduce the number of clip modules we had, but we have more contouring. So if our contouring is computationally expensive, we might want to clip the contour. So we've got to adjust from that, working out what is computationally cheap and where the large data is. So these people think they've got large data, but if the data is very easy, very easy to contour, it's going to contour fast. If you've got data that's computationally expensive to contour, it could be a very small data set, but it will be difficult to run interactively on your system. And then you would try and put the contourer very near the beginning of your pipeline. And that's the end of the presentation. So thanks to the N8 for hosting us. Thank you for the School of Computing at the University of Leeds for employing us, and thank you to EPSRC for funding me.